remember to keep your microphones muted during the talk so that we don't get too much background noise. If you have any questions throughout the talk, feel free to sort of jump in and interrupt, or you can post questions in the chat and I'll make sure that those get attended to. There will also be time at the end to ask questions as well, unless you're waiting for the end. So today's speaker is Ani, who is currently a PhD candidate at MIT working with Professor Anna Flevel. He got his bachelor's degree from Cornell in 2014. He will be on the postdoc job market this fall, so if anyone's looking for postdoc, please reach out to him. And with that, take it away.
Thank you. Thank you for the introduction, and I'd like to thank everyone that organized the seminar series for giving me a chance to present my research at this venue. Before I jump into my research, though, I'd like to acknowledge that today is Juneteenth, especially in light of recent societal pushes towards equality and social justice. I think it's important that we as astronomers are aware of this and continue to make the community an inclusive place. And I think the minimum is to acknowledge that this is an important day for those efforts. And with that, I'd like to thank everyone for coming to my talk. And today I'll be presenting some recent results on the detection of chemically primitive, extremely metal-poor stars in the outskirts of one ancient ultra-faint dwarf galaxy, and the implications this could have on our understanding of early galaxy evolution and early chemical evolution. And with that, I'd like to thank a number of collaborators that worked on this project, including a few people in the audience. I see many familiar faces and a few new faces, and I'm very excited to talk about this research. But before I go on, I would kindly ask people not to tweet results from this talk, because the manuscript discussing these results is currently under review at Nature Astronomy, and so the results are embargoed. But I'm happy to answer questions throughout the talk, or answer emails or questions at the end of the talk. I'm happy to discuss. Thank you. And to just provide a broad level overview of our understanding of dwarf galaxies, so we think and early galaxy formation, we think the earliest galaxies were small, and that larger galaxies formed through a hierarchical merging process of these smaller galaxies. And to illustrate this point, I have here a simulation from the Caterpillar suite, a dark matter only simulation of the formation of a Milky Way mass galaxy. The key qualitative takeaway I want you all to see from this simulation is the fact that smaller systems continually infall and accrete onto this larger system in the center until at z equals 0, which is today, we end up with a Milky Way-sized galaxy with many smaller systems surrounding it. And these smaller systems are generally older and are known as dwarf galaxies, and generally host older stellar populations. And a few of these galaxies are relic surviving galaxies from the earlier universe, from the earliest stages of galaxy formation, and therefore are interesting environments to study the chemical evolution of early elements. And to draw a connection between simulations and observation, here is a schematic of the Milky Way. When non-astronomers think about the Milky Way, most people visualize the disk, which is shown right here. But the Milky Way is actually embedded within a larger dark matter halo, which has a scale length 10 times the size of the disk. And within this dark matter halo, we see old stellar dark matter dominated systems that are dwarf galaxies. And these dwarf galaxies are analogous to those dwarf galaxies that I showed in the previous simulation, qualitatively analogous. And these systems generally host more metal-poor older stars and are environments in which we can study early chemical evolution processes. And to make this fact a bit more tangible, this is a schematic on how stars in dwarf galaxies or low-mass ancient stars can be used to infer the chemical abundances in the earlier universe. So suppose there is so from the left to the right, suppose we have an early star, or perhaps a population 3 first generation star. We think these stars were very massive and short-lived, but began the process of forming heavy elements from the primordial hydrogen and helium in the early universe. So throughout the lifespans of these stars, through nuclear fusion, and then at the end stages of their lives in their supernovae explosions, they generate these heavier elements that astronomers called metals. And they deposit these metals into their surrounding media. And then when the next generation of stars form from the gas that has been enriched by the heavier elements from these earlier generations of stars, a few of these stars may end up having low masses and therefore survive until the present day. And indeed, these are stars we can find in our own Milky Way galaxy today, and we can derive their chemical abundances through spectroscopy. And these are also stars we can find in dwarf galaxies. I mean, this is environment dependent, but essentially the bottom line is we can find these low mass relic stars from the early universe today. And we can derive their chemical abundances in their stellar photospheres using spectroscopy. And to first order, generally speaking, the chemical abundances in their photospheres is relatively unchanged to first order from the star-forming gas cloud that formed these stars. And so as a result, we can use spectroscopy of stars nearby, in nearby dwarf galaxies or in the Milky Way, to infer the chemical abundances of, that were present after the first generations of star formation or chemical enrichment. And to make this a bit more tangible, I'm displaying some spectra of stars of various metal contents or metallicities, just to show how observers infer these properties from observed spectra. And so first I'd like to introduce the concept of metallicity, which is the overall, which I'll use interchangeably with the iron abundance, which is given here as customary in the field, which is essentially the log ratio of the relative iron to hydrogen ratio of that star with respect to the sun. A metallicity of 0 means that star has the same relative iron to hydrogen ratio as the sun. And so this is a spectrum of a solar metallicity star. And one can see many different absorption features here corresponding to the presence of many heavier, relatively more heavier elements. As we go to lower metallicities, say a metallicity of -1.6 or -3, these absorption features become weaker as there is less relative presence of these heavier elements with respect to other elements, until all the way to a metallicity of -3 or -5, where these features become extremely weak. And what this generally means is that at lower metallicities, stars at lower metallicities formed when the universe was less enriched in heavier elements. So to first order, this is some sort of a look back time to first order. And what's a particularly interesting regime is the regime where stars have metallicities below -3 or generally below -5, largely because when you hit metallicities below -3, that means there were order few, not one, but relatively few progenitors, supernovae, that enrich the atmospheres of these stars. And below metallicities of -4 or -5, the chemical abundances of these stars can possibly be modeled as yields from single supernovae. So this is one direct way to infer early chemical evolution processes or yields using metal poor stars. And it's really interesting to study metal poor stars in dwarf galaxies, since the oldest dwarf galaxies generally host large populations of these metal poor stars that are involved in a somewhat self-contained environment. And so the interpretation of their abundances can be a bit easy, which facilitates the interpretation of these abundances of these stars. And to highlight the fact that this is not an abstraction, this is a schematic of all of the dwarf galaxies known around the Milky Way as of 2016. This is a rapidly growing field with at least a dozen dwarf galaxies having been discovered since then. So this graphic is already out of date. The key point here is that many of these dwarf galaxies are recently discovered ultra-faint dwarf galaxies. And by recently discovered, I mean in the past 15 years or so, with the advent of large-scale, precise photometric sky surveys. These dwarf galaxies are known as ultra-faint dwarf galaxies because, as their name implies, they are very faint. They have generally low masses, and they're very dark matter dominated. And they're interesting for these reasons. If you remember the simulation I showed a few slides ago, in which smaller galaxies merge to form larger systems, the low mass of ultra-faint dwarf galaxies and their old stellar populations might imply that these are surviving galaxies from the early universe, and therefore they're interesting places to study the chemical abundances of metal poor stars. In this particular talk, I will be focusing on the Tucana II dwarf galaxy, which is shown right here. Tucana II is a fairly classic ultra-faint dwarf galaxy. As I mentioned before, we think these ultra-faint dwarf galaxies are somewhat analogous to early galaxies, or perhaps the earliest galaxies that formed in the universe. They have low masses, which suggests there might be like early stages of the building blocks of the ladder to building larger systems. But also corroborating this is that their stars are generally very metal poor. The mean metallicities of these systems is around -2. By isochrone fitting, one can also infer that the stars in these systems are old, or about 13.3 billion years old. So these systems are really relics from the early universe, and the chemical abundances of their stars are therefore interesting to study in a early chemical evolution context. And so for this talk, I would like to frame the discussion, or frame these results, or couch these results in terms of two very broad questions. One is, what were the properties, or such as the dark matter mass, of the early galaxies that hosted this early chemical evolution? And perhaps can we infer this from the existing population of ultra-faint dwarf galaxies? The second question I'd like to pose is just related to what shapes these systems in the sense that would the prevalence of supernovae or galactic mergers shape the evolution of these early galaxies that hosted early chemical evolution? And these two things are fairly interesting and can be studied from ultra-faint dwarf galaxies due to the fact that these are relics from the early universe. But the real bottleneck in studying faint dwarf galaxies is, as their name implies, they are very faint, and therefore it is incredibly difficult to characterize their member stars. So as you might remember, I provided an introduction on how astronomers obtain spectra of stars and then infer properties such as their metallicity from those spectra. And so it is necessary in order to characterize the stars in an ultra-faint dwarf galaxy, to identify its member stars and then obtain spectra of those stars so that we can derive those properties and understand their early evolution. But this is difficult for ultra-faint dwarf galaxies because their stars are fairly sparse. Tucana II has a stellar mass of about 3,000, so there aren't really that many stars there. And then on top of that, what this means is that this is a plot from the detection paper of Tucana II. The key takeaway here is there is a statistical overdensity in the center of this plot of stars, but it is incredibly difficult to know whether any given star is actually a member of this dwarf galaxy. So it's possible to point a spectrograph at a star in this field of view, and then just observe a foreground star that just so happens to be in the field of view of the galaxy. And that makes these systems incredibly hard to characterize. And so generally, what is done is one takes spectra of a number of stars in the field of view of this dwarf galaxy, and from these spectra, one derives a radial velocity and an overall metallicity. And since the stars within the dwarf galaxy that are members are gravitationally bound, they'll have the same systemic radial velocity. And since these stars are ancient, they'll be chemically under-enhanced and have lower metallicity. And so one can make a simple radial velocity versus metallicity plot to identify members of Tucana II versus non-members. But for that, one has to obtain spectra of many stars in the field of view of the galaxy. And this is actually difficult to do with current telescopes, with 6-meter class telescopes. And that's generally because most stars in ultrafaints are very faint. And so many hours of spectroscopy is needed to get usable high resolution or medium resolution spectra. And the low probability of membership just means that it's difficult to identify member stars. And so, for example, this study by Walker et al. In 2016 observed, I think, obtained about 50 usable spectra, 50 to 70 usable spectra, and identified 8 member stars in Tucana II, which is a success rate of just over 10%, which makes these systems, which illustrates how difficult it is to characterize these systems. And so the motivation for this project here is, well, the following. The project I embarked on with my advisor, Anna Friebel, is, well, if there was some way to derive metallicities or overall metal contents just from imaging, could we perhaps image the region of an ultra-faint dwarf galaxy, derive metal contents of every star in the field of view, and that way we could make a cut along the x-axis here, just to identify member stars through a metallicity criteria from images, and that way efficiently find stars for spectroscopic follow-up. And that's the project we embarked on, which led to these results. And the way we did this was by using a telescope known as the SkyMapper telescope, which is an imaging telescope that has been used in searches for metal poor stars. And the reason this telescope is useful for searches for metal poor stars is that it has an imaging intermediate band V filter, which is metallicity sensitive. And what do I mean by that? What I mean is the filter is sufficiently narrow and encompasses a prominent absorption feature known as the calcium 2K line, such that the overall strength of the calcium 2K line actually affects the brightness of the star through this filter. And to illustrate that, I've shown the absorption lines of a -1 metallicity star versus a -3 metallicity star, the calcium 2 absorption lines. You notice there's a distinct difference in the strength of this absorption feature. What this means is that a metal poor star will appear brighter in this filter than a metal rich star. And so this way, one can quantitatively infer the metallicity of a star from using matching methods or modeling. One can quantitatively infer the metallicity of a star just by its brightness through this filter and several other imaging filters in the filter set because of the calcium 2K line. And that's where the metallicity sensitivity comes from. And so indeed, so there is a telescope with a metallicity sensitive imaging filter. And the other useful criteria in identifying dwarf galaxy members, as I mentioned before, is velocity information. And to further highlight that fact, let's say we point a telescope at a dwarf galaxy, we will see the dwarf galaxy, but we will also see foreground and background stars around this dwarf galaxy that are projected onto the same field of view of the system. If we were to obtain velocities, we would notice that the dwarf galaxy stars are gravitationally bound and have roughly the same systemic velocity, and foreground and background stars have randomly distributed velocities. And so on that note, what's really useful for this, for identifying dwarf galaxy members is also proper motions or tangential motions in the sky from the Gaia mission. And for the non-astronomers, the Gaia ESO mission has derived proper motions or tangential motions of essentially all stars in the sky above a certain brightness limit. And since we have these tangential motions, this can also, for a lot of stars in the field of view of these dwarf galaxies, we can also use that to identify likely members through a proper motion selection criterion or tangential selection criterion. And this is just an illustration of that, this plot. This is the proper motion in declination versus the proper motion in RA of many stars in the field of view of one dwarf galaxy with known members. And the key highlight here is the members of the dwarf galaxy cluster in proper motion space because they have the same systemic motion as opposed to non-members. And so this can also be used to identify members of ultra-faint dwarf galaxies and alleviate that membership selection problem. And so what happens when we tie this all together? So as I mentioned, we studied Tucana II using this method. So for Tucana II, we obtained deep SkyMapper images with the metallicity sensitive filter to derive metallicities of every star within a degree of Tucana II. And then we used Gaia proper motions to select likely members. And to illustrate and we also used a surface gravity cut, which I won't describe in this talk, but you can feel free to ask me about. And the three of these criteria together led to an order of magnitude improvement or orders possibly magnitude improvement in target selection efficiency. So these are likely members that would be found in Tucana, or that would be spectroscopically followed up in the 1 degree of Tucana II using a traditional isochrone selection technique. Using these three selection techniques combined, we essentially remove a lot of the foreground interlopers in the vicinity of Tucana II. And what's interesting is we recover the population of known members in the center here, but we also see stragglers that remain after applying all of these selection cuts out to 1 degree around Tucana II. And a natural question now is, well, these stars up to a degree around Tucana II have low metallicities and have proper motions that are consistent with membership of Tucana II. Could they just be random stars that happen to fulfill those criteria? Or are these stars actually members of Tucana II? And could they lead to, and could there be undiscovered features around this ancient galaxy that were being hidden by this foreground level that we were seeing before? And on that note, I should mention that since dwarf galaxies are so difficult to characterize, no member of a dwarf galaxy has been discovered beyond 4 half-light radii from the center of a dwarf galaxy. And very few stars are known beyond 3 or 2 half-light radii of dwarf galaxies. So I should just keep that in mind. So what we did was we went to a distance cut. So Ginny asked, did you consider a distance cut? A distance in terms of, so the surface from us, yeah, so the surface gravity cut that we used is some sort of a proxy for a distance cut. There was also an isochrone overlaid on the color magnitude diagram. And so at some level, that is also kind of like a distance cut, but not really. But the surface gravity cut excludes nearby main sequence stars that would be along the line of sight. So that is some proxy for a distance cut. So what we did was we obtained, I hope that answered your question. So what we did was we then obtained follow-up spectra of a number of these stars and to see if their radial velocities were consistent with membership and their metallicities. And what we ended up discovering is that Tucana II, this particular ultra-faint dwarf galaxy, is a more complex system than more morphologically complex system than previously thought. So these were the known members of Tucana II before 2018. I have overplotted the half-light radius of Tucana II, and so as is normal, there are 7 members known in the system, and they're generally all within 2 half-light radii of the system. The members we discovered extended out to 9 half-light radii from the center of the system, and so the blue data points here are the members that we spectroscopically followed up after identifying as likely members from the SkyMapper metallicity selection criteria and the other selection criteria that I had mentioned before. So these new stars are a new population of member stars around this one ultra-faint dwarf galaxy. There's an interesting morphological shape here in that the galaxy appears elongated in one direction. And so a natural question is, well, how does it get this shape? Could it be a result of tidal disruption from the Milky Way galaxy? And so to illustrate that point, one dwarf galaxy that is being disrupted by the Milky Way in a dramatic fashion is the Sagittarius dwarf galaxy, and it leads to these streams. This is a visualization, and it leads to these streams forming around the dwarf galaxy. What's interesting is we contacted Dennis Urkel at Surrey to model the location of expected stars if this galaxy were being ripped apart by the Milky Way, tidally disrupted. And that is what is shown by the arrows here. Oops, by the arrows here. So the location of tidally disrupted stars, if Tucana II were being tidally disrupted, would be along these arrows. But the, sorry about that. But the newly discovered member stars are not along this tidal track, which is puzzling. These stars also don't show a velocity gradient, which is one criteria to check whether the system is tidally disrupting. So it seems likely that, it seems unlikely that the location of these stars is actually due to a tidal disruption signature of the galaxy, given that they don't lie where we expect debris to be, and there's no velocity gradient present. So the location of these stars might actually be an intrinsic property of Tucana II, as opposed to some intrinsic influence by the Milky Way. And so what does that mean? Well, if we then consider that these stars must be are members of the system and therefore, and are not tidally disrupting and therefore gravitationally bound, the furthest star from the center of Tucana II is 1 kiloparsec away from the center of the system. In order to gravitationally bound a star 1 kiloparsec away from the center of the system, in order to have a tidal radius that extends this far out of Tucana II, then the enclosed mass within this bound, within this radius of Tucana II, must be at least 10 to the 7 solar masses. And this is, and if you compare this to the mass within the half-light radius that has been measured via, or that has been derived via velocity dispersions, this is at least a factor of 5 higher than the mass within 1 half-light radius of the system. And the stellar mass of Tucana II is 3,000 solar masses. So what this means is that if we assume these stars are bound to the galaxy and not tidally disrupting, then there must exist a massive dark matter halo around this system. When I say massive and extended, it just means that there perhaps is a halo that was not detected before. I mean, so this particular mass bound is perfectly compatible with this dwarf galaxy having an NFW profile, which is the density profile that larger dark matter density profile that larger galaxies show. So it's not like this is an abnormally large dark matter halo. It's just that the only dark matter mass measurements of ultra-faint dwarf galaxies were out to a half-light radius before. So this is evidence that they may inhabit an extended dark matter halo, much like larger galaxies. So this is something. So this is one thing that's interesting if one wants to model early chemical evolution in these ultra-faint dwarf galaxies. But in fact, I think most simulations of these systems already assume that such a dark matter halo existed, and this is just empirical proof of that fact. Some empirical evidence supporting that fact. Secondly, an interesting property we discover that is relevant to chemical evolution studies is the fact that the most metal-poor stars in Tucana II actually lie in the outskirts of this system. So this plot on the right is the metallicity of each member of Tucana II as a function of its distance from the center of the system. Previously, stars only within 2 half-light radii, or out to here, were essentially known in Tucana II. Now we've detected stars out to 9 half-light radii, and we find that the stars in these outskirts are generally more metal-poor than the stars in the core. And this is puzzling. And as you can see, the most metal-poor star is the furthest away from the system, the center of the system. And this is puzzling. What could possibly cause this kind of metallicity gradient? One natural explanation is that a galaxy merger in which two different galaxies merge and one galaxy deposits stars in the outskirts of the other, much as the simulation I showed at the first slide of this talk, the formation of hierarchical merging of larger galaxies. That is one way to cause a differential in the metallicities that might look like a gradient. We do expect small galaxies to undergo mergers of some sort. This is a plot from Ray et al., where they simulate the formation, 2019, where they simulate the formation of the evolution of an ultra-faint like dwarf galaxy. And the mass growth at the end is driven by mergers with other small systems. And in fact, in their the text, they explicitly mention that the bulk of one galaxy they follow is grown by dry mergers, depositing stars in the galaxy's outskirts, and making this galaxy look bigger, and expanding its effective radius. And indeed, that might be analogous to the signature we're seeing in Tucana II. And one other way this kind of metallicity gradient in morphology could be formed is through some sort of supernova feedback. There is some evidence in simulations that UFDs have bursts of star formation. If this is true, and this is just a toy model I have, the toy model I'm presenting, if we have the first generation of star formation in the center of an ultra-faint dwarf galaxy, and there's a supernova that dynamically heats these stars, then gas collects in the center of the system and forms stars again, you might end up with a metal-rich population, a more metal-rich population in the center, and a more metal-poor population in the outskirts. There are a number of physical, I guess, checks one needs to do before thoroughly presenting this argument, such as what kind of enrichment would occur, what kind of metallicity gradient would one see, was the magnitude degree, and would you get star formation in a successive generation? This is just something I'm posing, and I'm sure modelers will have some insights onto this. And finally, so the other important part I'd like to highlight is that the most metal-poor stars in this particular ultra-faint dwarf galaxy were in the outskirts of the system. This is interesting because modeled metallicities of stars in ultra-faint dwarf galaxies from JINA-CEE, for instance, at the bottom here are ultra-faint dwarf galaxy-like halos. There is a tail of metallicities that should extend below a metallicity of -4. But out of this, I think, over 60 stars with high-resolution chemical abundances in ultra-faint dwarf galaxies, and I think at least 150 around stars with medium-resolution metallicities, there have been no observed stars with metallicities below -4 in ultra-faint dwarf galaxies. And this is speculative, if the result we're seeing with Tucana II is a generally true property of ultrafaints, where their most metal-poor stars are in their outskirts, then this might actually make sense because the most metal-poor stars in ultra-faint dwarf galaxies may have been missed. And this is particularly interesting beyond just filling up a completeness, because the authors of this study suggest that stars with metallicities below -4 in ultra-faint dwarf galaxies are essentially externally enriched, are stars in a primordial halo that have been externally enriched by neighboring halos. And that's how one gets these very low metallicity stars in ultra-faint dwarf galaxies. And to highlight that fact, this is just a simulation of external figure illustrating external metal enrichment from Smith et al. 2015. I believe Rana also gave an arena seminar. Rana Edzadine gave an arena seminar quite recently on external metal enrichment from neighboring galaxies. But the key takeaway here is the following. If we look at this collection of two galaxies here, we have one host galaxy and we have a neighboring galaxy. A supernova occurs, an early supernova occurs in this galaxy, and there's some metal outflow to a neighboring galaxy enriching that galaxy too. And since there's a fewer absolute number of metals flowing into this system than perhaps that enrich the core system, the overall metallicity of the neighboring system is lower, as this plot suggests, about -4 to -5. And so one might get very low metallicity star formation in ultra-faint dwarf galaxies through this external enrichment scenario. And so perhaps seeing a -4 star in an ultra-faint dwarf galaxy would be further evidence for this. And this is just speculative, but again, it's just suggestive of the kinds of things one can do if one can characterize these systems, or interpretations, one can characterize these systems in a more complete manner. And so and this is just further highlighting that fact. And to tie this back to the two questions I presented at the beginning of the talk, which were essentially what were the properties of early galaxies as inferred from relic ultra-faint dwarf galaxies around the Milky Way today, and to what extent do various processes shape these systems. We have some evidence from our study of Tucana II that the earliest galaxies probably inhabited massive extended dark matter halos, much as is assumed in theory, and much as as we see in larger galaxies. This extended stellar morphology and metallicity gradient we're seeing in Tucana II might be evidence that mergers or feedback may have shaped these early systems. But the real question here is, it's entirely possible that Tucana II could be some sort of outlier. And a question now is, do the population of ultra-faint dwarf galaxies show this extended morphology? Or did I perhaps get lucky in picking the one ultra-faint out of, say, 25 that just happened to be this way for our random study? And that's a useful question to ask. And so to start answering this question, um, I've been working on a project to essentially survey all the ultra-faint dwarf galaxies in the southern sky using a metallicity sensitive imaging filter that I helped install on the Magellan telescope with the help of Steve Schechtman from Carnegie Observatories. And so to just go over how these imaging metallicity sensitive filters work, this is the blue lines are a spectrum of -1, metallicity -1 star, and -3 star in the neighboring plot. This bandpass here is the bandpass of the metallicity sensitive sky mapper filter. And you can clearly see here that the calcium 2K lines affect the overall flux through the filter as the metallicity varies. And the imaging filter we have installed on the Magellan telescopes is actually, is shown in red here. And it's actually a narrower filter. So the signal we see from the absorption of the calcium 2K lines will actually be stronger in this filter relative to the sky mapper filter, or at least comparable at minimum. And an interesting sociological point is that this Magellan HK filter is actually the same filter that Tim Beers, George Preston, and Steve Schechtman used in their survey for metal poor stars almost at least 3 decades ago now. So it's interesting that this filter is making a comeback in these photometric metallicity searches. And so to quantify this fact that this new HK Magellan filter, the metallicity sensitive Magellan filter that I'll call the HK filter, is metallicity sensitive, we can forward model the predicted fluxes through this filter over a range of stellar parameters and see whether the metallicities of these synthetic spectra, these model stars, separate in some color space where one color term includes the flux through this metallicity filter. So this is the contour plot I had made for the sky mapper filter to show that it is metallicity sensitive. And you can see that the metallicities, various metallicities separate in color space. And this is an indication that these stars are metallicity sensitive. If I do the same exercise with the Magellan HK filter, qualitatively the same result occurs, where we see a separation in color space over different metallicities using this HK filter. So at minimum, this filter is quantitatively sensitive to the overall metallicity of stars. And the reason we went through this trouble of installing this filter on the Magellan telescopes is because the Magellan telescopes are big and it's a great site for imaging. So for instance, with SkyMapper, it took us 13 hours of imaging data to characterize one ultra-faint dwarf galaxy, Tucana II, down to a certain magnitude limit, 13 hours for one dwarf galaxy. Given the larger, and so SkyMapper has an aperture of 1 meter, 1.2 meters, I believe, and the seeing conditions are slightly worse with the telescope. With the Magellan telescopes, we can do the same analysis with just 15 minutes of imaging data on one ultra-faint dwarf galaxy. So this is an order of magnitude gain in observing time to characterize ultra-faint dwarf galaxies, on top of the order of magnitude gain we get in selection efficiency by using this imaging filter. So this is really exciting. And just to show that this actually works, we obtained data of 6 dwarf galaxies in August through this imaging filter. And what you can see here is just pilot results for one system, Sagittarius II. And the key takeaway here is I have the metallicity sensitive color plot on the right, where the known members of Sagittarius II clearly separate from the foreground population. So at minimum, this filter can be used for qualitative selection of dwarf galaxy members to efficiently identify member stars. And so on that note, we have been allocated 3 nights on the Magellan Bada telescope for imaging ultra-faint dwarf galaxies to search for any possible candidate members in their outskirts in fall 2020. And what's interesting is I mentioned with 15 minutes, we can do this kind of analysis for one dwarf galaxy. And so with 3 nights, I presented results on Tucana II. With 3 nights, we can do every dwarf galaxy in the southern hemisphere in this way. And so I should emphasize that this will be the first step in a selection process in the sense that we'll have to do spectroscopic follow-up of candidate members identified through this selection procedure. But this is an exciting way in terms of searching for extended halos around these relic galaxies to better characterize them. And so in summary, the key result I presented here, which I'll remind people if they join at the end, is currently embargoed. So please contact me with questions, but try not to tweet about the results, is that we detected extremely metal poor stars out to 9 half-light radii away from the center of an ancient ultra-faint dwarf galaxy. This extended morphology and metallicity gradient implies that there is likely an extended dark matter halo around this ultra-faint dwarf galaxy, and some sort of mergers or supernova feedback may have shaped the evolution of this particular system. The most chemically primitive stars in this particular system lie in its outskirts. If this is true of all ultra-faint dwarf galaxies, then this means that further analysis in their outskirts is needed to get a more complete analysis of their metallicity distributions of their stars, and therefore, which might have implications for interpretations for instance, external chemical enrichment. And this just opens the possibility of studying possibly halos or extremely metal poor halos around these relic galaxies, which might be what we're seeing around Tucana II, in the sense of extremely metal poor stars at a very large distance from the center of the system. And to answer these questions, there is upcoming work, imaging work in the fall that will test whether all southern UFDs host these spatially extended populations, or at least it'll identify such stars for spectroscopic follow-up for further characterization. And with that, thank you for coming to my talk, and I'm open to any questions.
Thank you for the great talk. This is such an interesting result. This is going to be so cool. So yeah, there's already a question in the chat. So can you read that, or do you want me to share it?
Would you mind sharing it? Sorry.
No worries, yeah. Could you please explain a little bit more about how you derived the log G and how accurate? Also, yeah. Is this methodology could potentially be applied to a number of ultra-faint dwarfs? Why would you choose Tucana? And are there special conditions to observe it with SkyMapper, maybe?
Yeah, so I will, so for the first part, I'll answer the surface gravity selection by saying that the SkyMapper U filter and the SkyMapper V filter bracket the bomber jump, which is sensitive to the overall surface gravity of the star. So the relative flux through the U and V filter is a proxy for the surface gravity of the star. And you can do the same thing I did here with the metallicity by forward modeling the predicted metallicities with synthetic spectra, by forward modeling the predicted surface gravities, and get the same separation, but in a different color space. The precision is good enough, I think, for a qualitative cut to remove to separate main sequence and giant stars, but I don't think it's sufficiently precise to like quantitatively get a surface gravity. But it's enough to separate giants from foreground main sequence stars, which is what we use in this analysis. So from my understanding, Tucana II was somewhat randomly selected to be observed at SkyMapper. It's accessible from the SkyMapper site in that it's in the southern hemisphere. It also, I think, has the largest or one of the larger half-light radii known of ultra-faint dwarf galaxies. And the SkyMapper telescope has a large field of view, so it seemed kind of optimized to study this particular galaxy. But the data was actually given to me, so I don't know what went into the observing proposal, but I imagine it was some combination of those two things.
All right, we have another question. The lowest metallicity stars in the Smith et al. Simulation ended up being 1 kiloparsec from the center of the more massive galaxy. Did that simulation require a massive dark matter halo as well?
Sorry, low sim. Ended up 1. So I don't know specifically about this simulation, but I think if one assumes that, I think it's generally assumed that these galaxies inhabit larger dark matter halos in simulations. So I assume that was also the case in that simulation too. I think the main thing is there wasn't an observational signature of perhaps these systems inhabiting such extended halos until this particular result. So I assume that was assumed in the simulation as well. I hope that answers your question.
We also have a question from Benoit. Very nice talk. Once additional members of ultrafaint galaxies will be identified, like in Tucana II, will there be follow-up studies to derive their elemental abundances? And would that represent too much telescope time?
So there will definitely be follow-up time to observe their elemental abundances. What's really neat about this Tucana II result actually is that the furthest stars are actually about as bright as the stars at the center of Tucana II. So it is possible to, and we have an observing proposal in the fall to derive detailed chemical abundances of these most distant stars. So what's really neat is that we can actually find bright stars that are members of dwarf galaxies that were missed by previous searches. It's still expensive to get spectra of these stars, but it's not prohibitively expensive to get a spectrum of these stars, possibly. Yeah, but I mean, I think in general, it's expensive to get spectra of ultrafaint dwarf galaxy stars, so it'll be a hard thing to do, but it's still feasible.
All right, any more questions? Okay, as you get spectra and chemical abundances, will they be available in JINA base?
Yeah, I would assume so. Once as they are published, they will be put on JINA base.
Once things are no longer embargoed, I imagine. All right, any more questions? I have sort of a naive theorist question for you, if I'm taking it. I've never heard of these metallicity-dependent filters before. Is there anything that can give you sort of a false signal for metallicity, if that makes sense?
Yeah, so lots of things can. So if we have a very young star that's recently formed, one will actually see emission in the calcium 2K region.
Okay.
So as you can imagine, that'll do something strange with the observed fluxes. But there are other color cuts one can use to alleviate that. The other thing too is if you make the filter too narrow, a hypervelocity star, I don't think that any of the filters I'm using are that narrow, but a hypervelocity star could get redshifted outside the, and so it would look very metal poor, but it would actually just have absorption features somewhere outside the filter.
That's interesting. Any more questions? All right, if we have no more questions, I'd like to thank the speaker for joining us and sharing this work. This is really great. And I'm looking forward to seeing what's next. And hopefully everyone can join us again. We have another speaker in 2 weeks. And we'll have the seminar series again. All right, thank you so much.
Thank you.